Welcome back. Happy Wednesday. I hope we stayed safe yesterday. Today is the very last day of new material for the entire semester. We will cover a couple of theorems about definite integrals. I will hand out quiz number 5 during class. You'll take it at home individually and hand it back to me first thing Friday. I handed out the last project last class. It is due at the start of the final exam, but you can do it early and turn it in anytime. In fact, I recommend you turn it in early if possible. Final exam is coming up 1 week from today, right here in this classroom, 10:30, although we'll talk about that. I'll have you start at 10. Monday is a regular class day, yeah? That'll be a review day. So that's what we've got coming up. Friday and Monday is just review days, and then the exam is Wednesday. Any questions on the calendar? Okay, so let's get started here on page 77. All right, here we are, top of page 77. In this class, we discover several theorems about definite integrals and investigate the area between two curves. Number 1, what if the limits of integration of a definite integral are both the same number? So in this example, we've got this integral f of x dx, but we're going not from a to b, two generic numbers, but specifically from a to a, the same number to itself. Now we know that the integral represents area below the curve and above the x-axis, and then between these two vertical lines at x equals a and x equals b. Well, what happens to that area if a and b are exactly the same number? It's 0. So that's what we define this thing to be. So anytime you're faced with an integral where the two limits of integration are the same, your answer is 0. It doesn't matter what the function inside here is. Okay, what if the smaller number is on the top? Every integral we've done so far has had the smaller number on the bottom and the bigger number on the top, but it doesn't have to be that way. So for example, what is the value of this integral? It says the integral from 2 to 0, smaller number on top, of 6 dt. Okay, so let's come back to that and first define this one. And we know how to find this one because here the numbers are in the quote right order. So 0 to 2. What's the graph of y equals 6 look like? Just a horizontal line, and it's up 6, and we're going from 0 to 2. So what's the area there? 12, right? It's just a 2 by 6 rectangle. So this one here, the answer is 12. Now let's imagine that this integral represents the distance a runner travels in 2 hours if they are running 6 miles an hour. You buy it? Constant 6 mile an hour speed. The area under that velocity curve is the distance traveled. And so we went 12 miles. That makes sense. 6 miles an hour for 2 hours. But then we can think of this integral from 2 to 0, again, that's the wrong order, as representing the distance traveled in reverse. You just like watching the movie backwards. So you wouldn't say the person traveled 12 miles forward. You would say they traveled 12 miles backward. So what do you think is our value of that thing? Negative 12. That's it. And so anytime you want to swap the numbers on the integral sign, you just make it the opposite sign of what it used to be. So if you have the integral from b to a and you'd rather have the integral from a to b, no problem. Switch those limits, but put a negative sign in front of the whole thing. Okay, couple of examples for us to apply our new rules here. Okay, first one, integral from 3 to 3 of x plus 2 dx. It's 0. It's the easiest question on the page because the 3's are the same. This is 0. Okay, let's take a look at this integral. It's the integral from 1 to 0 of the square root of 1 minus x squared dx. Now I've given you a picture here. This is the graph of f of x equals square root of 1 minus x squared. It's just part of a circle. And in this case, we're going between 1 and 0. So what fraction of a circle are we talking about? That's a quarter. This is the quarter circle that we're thinking about. And so then the area of a circle we know is pi r squared, but this is a quarter of the circle. So divide by 4. What's the radius for our circle? That's 1. So pi times 1 squared over 4, or simply pi over 4. Okay, so the area of that quarter circle for sure is pi over 4, but we need to relate that to the integral that was given to us. This was the integral from 1 to 0, and we have to recognize there's something suspicious there in that the smaller number is on top and the bigger one is on the bottom. So before we use the work we've done over there, we're going to say, hey, I'd much rather deal with this integral. So go ahead and copy the whole thing, but swap those limits of integration. And at the moment, I have an equals sign there, but they're not equal yet, not until I pay for it. So how do I pay for it and make them equal? Put a negative in the front. Now they're equal. And so I'm copying my negative sign. What's the value of this integral now that the things are in the traditional order? Pi over 4. So our answer here is just negative pi over 4. Okay, more properties. Okay, number 4. It's got 4 different things for us to fill in. The first one says the integral from a to b of f of x plus g of x dx. Now f of x plus g of x, it looks like 2 functions, but it's really 2 functions added together, which we can think of as just being one sort of bigger function. And it turns out that if you think about areas, you can come to this conclusion that you can actually separate this and do your 2 separate areas separately and then add them up at the end. Said another way, you can separate any integral that has addition inside of it in the same way that we separated derivatives that had addition. Yes? Like if I said, what's the derivative of 3x squared plus 5x? In your mind, you're already thinking of doing those as 2 separate derivatives, right? Well, it's the same thing here. If you have an integral with a plus sign in the middle, you just separate, you do your 2 separate integrals, add up at the end. Part B, it's the same thing, but with subtraction. I'll be lazy and just put a subtraction sign. So addition and subtraction, very nice for integrals. Part C says that we're just integrating a constant dx. Now we've done one of these earlier today. The integral of 6 became 12. Why was it 12? It was 6 times 0 to 2. That was a difference of 2. Okay, so this is just generalizing that. So this is still a rectangle. What's the area of the rectangle here? It's not 2c. That's it. Height is c. The width, the horizontal, is b minus a, whatever the difference is between those 2 limits of integration. Okay, and then part D. Part D is kind of wonky. It says the integral from a to c of f of x dx plus the integral from c to b of the same f of x. It's not 2 different things like f and g before. What's different is that on the one integral we're going from a to c, and the other integral we're going from c to b. Let's take a look at this picture here in the lower left. Shade in the area that is represented by this first integral. It's the integral from a to c. Go ahead and shade that part in. And then separately, this says plus the integral from c to b. That's a different area. Go ahead and shade in that area in this picture. And we can see that we were kind of silly to stop this integral at c, right? Couldn't we have just done a single integral that would capture the total area in one shot? Integral from where to where? A to b of the original function. What did I switch? Is the ACB? Yeah, C is not really important. Like our traditional is A and B, so I just wanted a standard AB over here. Yeah, so there aren't going to be too many times where we have 2 integrals added up like this and we combine into one, but there will be times where we'll have a single integral and it makes sense for us for whatever reason to split into 2 integrals. No problem. You can split any place you want and then just add up the 2 integrals. Okay, number 6 says evaluate this thing by hand and then we'll check our answer on the calculator. Okay, so let's use our fancy new rules. So the first thing I see here is that this is a difference of 2 functions. And so we're going to split this up and write 2 integrals with a subtraction in between. So the first integral is just integrating 5. but every integral needs to have a d something, so that's 5 dx. The other integral is 3 square root of 1 minus x squared, and it also gets a dx. And what do we do with these two integrals? We subtract them, because that was our property B that says if you have two things subtracted in the integral, you can do two separate integrals and subtract them at the end. Okay, and this integral right here looks like this property that's just off the screen. It's just integrating a constant. What's the area here? Let's use that formula, even though you could just write the answer. It's 5 times what? 1 minus 0. That's it, okay? So integrating any constant, really easy. It's just a rectangle's area. Minus. Okay, there's a 3 sitting in front of this integral. In fact, I want to apply a property that I'm pretty sure is not on your page. 3c. It's not. How is it not there? All right, any guesses on what we can do with this 3? We can pull it to the front of the integral. It looks like this. I'll put a multiplication symbol there. Square root 1 minus x squared dx. Okay, so why can we do that? Well, it just works. I should have written this. I should have written this on the paper. So here's the property E from up above. Integral from a to b of a constant times a function is exactly the same thing as the constant on the outside of the integral, with the function still left inside. Okay, somehow I omitted that one, but it's still true. And this is how we apply it, is we just pull that 3 right outside and we'll multiply at the end. Okay, let's finish our calculation here. 5 times 1, that's just 5, minus 3 times. Now this integral is one we've seen earlier today. Normally it would be hard, but in this case we know the answer. What is it? That's just pi over 4. That's the one that we saw with the quarter circle. So that's our answer, 5 minus 3 pi over 4. Yeah, Aaron. The which one? Yeah, this is the quarter circle that we saw in the picture at the top of the page there. Okay, so I said we could check our answer, so let's check our answer. You don't have to do this, you'll have practice in the activity. But if I do math 9, so the function we were integrating was 5 minus 3 square root of 1 minus x squared. Comma, now the notation in this system is you just put the variable there, comma, and then you do the lower number, comma, the bigger number. I didn't say that right. The lower number, comma, the higher number. Doesn't matter which one's bigger. Okay, so when we ask the calculator to do all of this stuff, and I will tell you the calculator doesn't know any calculus and it doesn't know any of the things that we just did. It is literally drawing thousands of rectangles, thin rectangles to try to approximate that curve, right? There's some function, some curve up there, and it's approximating the area with lots and lots of rectangles. How do I check and see if our answer matches this one? Yeah, we're just gonna type in our answer, right? 5 minus 3 pi divided by 4. Okay, good. Which answer is more accurate? Top or bottom? The bottom is like 5 minus 3 pi over 4 is the right answer. This is the best decimal approximation the calculator can give us. Here, there is some error because it's using only 1,000 rectangles and not infinitely many rectangles, right? There's not a lot of error. Where does it first change? I guess it's this digit right here. We have a 5, they have a 1, right? So it's not bad, but every time you type in this FNINT, there's bound to be error because it's just approximating. Okay, so the activity starts on the next page. Go ahead and jump in and I will walk around.